Uranus and Neptune. Welcome to the episode on the last planet in the solar system from the Sun, which is planet Neptune, the 8th planet. I think we all know what happened to Pluto. Something was said on the Shumba for Creative Space YouTube channel on one of the shorts. There's a comment that was put there. I think we should all go and read it. Very informative. Okay, so that's the reason why Pluto was demoted. But we have this planet which becomes the 8th planet, which is planet Neptune. Okay, so we start by looking at the orbital period and the semi-major axis, the formulas of the two variables, and we see that we derive them from the Kepler's third law as always. So let us get into how we calculate it, but before we get into that, just go through how we derive those and read Kepler's third law so that you understand where we're getting these variables. And then now let's go on to look at the Neptune's orbital period. Okay, so we saw the Kepler's third law, we read it, and we found that one of the important variables is the orbital period, and that's what we're calculating here. And we're going to calculate it in Earth years, as you can see written there, which means it's relative to our time. We are not saying it's the time that's at Neptune there. We are talking about the time that we have here on Earth with our own units and our own perceptions. So our t will be equal to 2 pi multiplied by the square root of that, which is basically the semi-major axis to the power of 3, which is cubed, over the gravitational constant, that's capital G, which is 6.674 times 10 to the power negative 11, multiplied by the mass of the Sun, which is 1.989 by 10 to the power of 30. You're going to see these values popping up quite a bit in this video. And the semi-major axis is supposed to be in meters. That's according to the standard rules of calculations, which we call the SI units, the International Standard Units. And then we then get our answer in seconds, which is 5,205,807,998 seconds. Then we divide that by 60 seconds and by 60 minutes and by 24 hours by 365 and a quarter days. That's the 25.25. I think I talked about it many times. That 365.25 means 365 and a quarter days. And then you see that we multiplied all of them, which is just a shortcut, but you can divide by each. You can divide those number of seconds by each. Whatever answer you get, you divide by the next, divide by the next, divide by the next. So divide by 60 seconds to get minutes, divide by 60 minutes to get the hours, and then divide by 24 hours to get the days, then you divide by the days to get the years that you're looking for. And that's when you then get the 164.96 years to 2 decimal places. That's the number of years that Neptune takes to orbit the Sun or to go around the Sun. When Earth takes 1 year, Neptune has to take 164.96 years. Quite a long time indeed. Okay, now we move on to calculating the Neptune semi-major axis using that formula that was derived in the first slide that we looked at. So the definition of the semi-major axis is at the top there in the semi-major axis. Basically, it's like the half of the diameter of a perfect circular orbit. Let's assume it that way so that it makes sense. So which requires us to use another formula that we're going to use after this one. But let's first look at this one. You can use both formulas to confirm your answer. As you're going to see, we're supposed to get the same answer, so you need multiple formulas so that you can confirm if it is indeed correct or accurate. If it's not, then it means something is wrong, because both formulas are bringing out the same answer. So with this formula, we're going to substitute our values. We have the period, which we calculated, which was in seconds. We're using seconds here. Remember, in International Standard Units, which is SI units, we use it in seconds, not the 8 years that we calculated, but we use the seconds, which are 5.2058 by 10 to the power of 9 seconds. And then we cube root everything. Remember the GM that we looked at with the capture time being the mass of the sun to the power of 30 there, and then we divide by 4 pi squared, and then we get our answer, which is 4.499995391 by 10 to the power of 12, and then we divide that by 1000 meters to get our kilometers, which is the answer that you see at the bottom left side there. And then we want to convert that into astronomical units, rather, so that it's in terms of astronomical units. So we say 1 meter is equal to 6.685 by 10 to the power negative 12 astronomical units, which is written in brown there at the top there. And then we therefore multiply that value in astronomical units by that value that we got in kilometers, or rather in meters. Remember, we use standard international units, or international standard units, in our calculations. And then we get 30.0825 astronomical units, which is approximately 30.08 astronomical units to 2 decimal places. That's in terms of astronomical units, the same axis. So I would also want you to look for the aphelion and the perihelion, which is the apsis and the periapsis of Neptune in that orbit, in terms of astronomical units, using the same method that we used to convert the same axis into its astronomical units. Okay, so let's look at the formula so that we confirm our answer. We say our same axis z is equal to a plus p, which is the aphelion plus the perihelion, divided by 2. And that's where we then say 4.54 times 10 to the power of 9, which is, you see, it's written up there is 4.54 billion kilometers. That's how it is expressed in terms of indices. Then plus 4.46 by 10 to the power of 9, which is in terameters there because of the space in the diagram, so that's why it's in terameters. But it's basically the same thing, divided by 2. And then you get your 4.50 by 10 to the power of 9 kilometers, which is what we got previously. And then we convert to astronomical units. We then multiply like we did. Then we get our 30.0825, which is approximately equal to 30.08 astronomical units. Basically the same answer, which means we did correct calculations, which proves that we are very good mathematicians. Let's look at one of the easiest calculations that we always look at, which is the eccentricity of the orbit of planet Neptune. You can read the notes in white there to understand what eccentricity is, and then we find that we express it in terms of epsilon, or rather as epsilon, and then we say epsilon is equal to 1 minus 2 over that fraction plus 1, and the fraction is the aphelion, which is 4.54 by 10 to the power of 12 meters, over 4.46 by 10 to the power of 12 meters, which is the perihelion at the bottom there, plus 1, and then we divide that into 2, and then we get our answer in the brackets there, and then we say 1 minus that, and then we get our eccentricity, and then our eccentricity will be equal to 0.008 recurring, and then that will be equal to 0.0089889, yes, 889 to 3 significant figures. If it is 89, then it is to 2 significant figures. Okay, so if you look at that eccentricity that we have calculated, it's very close to 0. And as you see in that note, it says on the last sentence, when eccentricity is equal to 0, the orbit will be a perfect circle. So when you look at the diagram that's at the top left corner there, that orbit in white is an oval shape. That's nowhere close to being a circle, a perfect circle, which means that that is not the correct depiction or the correct illustration of the eccentricity of Neptune, or the orbit, the shape of the orbit of Neptune. As we have calculated here, it's supposed to be close, very close to being a perfect circle, since our value is very close to 0. So don't assume that that one is probably more than 0.4 in terms of its eccentricity. Okay, now on Neptune's orbital speed, we know we are going to start by looking at the gravitational force and the accelerating force, which are the two important forces which can help us to find this variable, because one of them contains the speed, which is the accelerating force. Then the gravitational force, we just use it as well because it contains some other variable that is also contained the accelerating force, which is the mass of the smaller object, which is Neptune in this case. and then it also has the force, which we can say is equal to the accelerating force. So if the two forces are equal, that's how we get that variable, which is v bar, which is the average speed. Then we say where g is the gravitational constant, as we all know now. M is the larger mass of the sun. It's not always the case. That's why it's highlighted in our case, the mass of the sun. It's not always the case that is the mass of the sun. You're going to see that when you look at surface gravity of Neptune. There's another mass that we're going to use there. And then we have the same major x, which is z, which is the proposed separation between Neptune and the sun. That's not always the case as well. We might use r, which is the radius of Neptune, as you see in the graph, when we're calculating gravity. You're going to see that. And then we have, let's find v bar, which is the average orbital speed, and that's how we then come up with that expression: v bar is equal to the square root of gm of a z. And then we say v bar is equal to the square root of g, which is 6.674 times 10 to the power negative 11 by the mass of the sun, which we now know, that to the power of 30, over 4.50 times 10 to the power of 12, which is the same major axis in meters. And then we get that 5,431.3056 meters per second. That's the unit for speed, meters per second. Then we divide by 1000, so we get kilometers per second, which is 5.43 kilometers per second, to 3 significant figures. Okay, now let's look at Neptune's radius. So you may be wondering why in some of the videos we've been using the volume of a sphere to calculate or rather to derive the formula for the radius, and make r the subject of the formula, and then we calculate the radius, and not use other formulas. We can use other formulas like the surface area, circumference, and all that, but let's just use this one. I find it fascinating to use. It's a bit complex compared to the others, so let's use that one, just so that if you get the easier ones, at least you're able to derive and calculate. And then we see we are going to base this according to resolution B5 of the International Astronomical Union, that talks about what is expected of a planet in order for a planet to fit the criteria of being a planet, because the term planet was redefined, and the components of that definition were stated in the resolution B5, which is a document that was released. You may need to search for it on the internet, or I can provide the link in the description. So here is a way of computing the radius after rearranging the formula of the volume of a sphere, which you can see at the bottom left corner there. Then we get our r is equal to the cube root of 3 over 4 pi multiplied by v, which is the volume of Neptune. Then we see our volume of Neptune, we substitute there 6.253 by 10 to the power of 13. Then we get our 24,622.5639 meters, or kilometers rather. And the reason why I'm saying kilometers, as you can see, our the value of the volume is in cubic kilometers. So when you then cube root that cubic kilometers, you then get kilometers. That's why I'm saying kilometers. And as you can see, it's approximately equal to, the radius is approximately equal to 24,623 kilometers. But as you can see, with the planet, it's not always a perfect sphere. It can bulge out a bit. So there are different radius that you can get. Rather, we call it different radii. Yeah, that's the plural radii. My apologies for that. So the different radii that you're going to get, one can be along the equator, the other one can be along the poles, the other one can be diagonal, whatever. How you are going to calculate, how you are going to see those, the radii. So it differs, but this one is the mean. We call it the mean radius. So it's like the average of all those. So this one is quite easy. There's only one thing to substitute there, which is the r. So just substitute to the radius that we calculated, then you get your answer 7.62 by 10 to the power of 9 square kilometers. Okay, now we look at the mean density of the planet. So we say the density of a solid or an object is equal to mass over volume. It's different from a liquid, because a liquid you have, you can say it's pressure of the gravity multiplied by the height of, or rather the depth of the container of that liquid. That's how you get your density. That's another way of getting density, but in terms of the liquid. Here we are looking at a solid, so you can say it's mass over volume, and we can express it in term as rho. Yes, that's the symbol that we can use. You can use any other symbol, but in our case we're going to use rho, the Greek letter that you can see in white there. So we start by trying to convert the values that we have for the mass and the volume of Neptune. So for the volume, our conversion rate is 1 kilometer is equal to 100,000 centimeters. So we have to multiply the cubic kilometers that we calculated, or rather that we used in our calculations, which is there, and then we multiply it by 100,000 cubed. So because we should convert it using the cubic centimeters, and then we get that answer there in cubic centimeters. And then we also have to change the mass, which is in kgs, to put it in grams. So the reason why I'm using grams per cubic centimeter is because that's how it's expressed in some sources, so that when you see those sources you look at them and you see how they came up with that value that we're going to come up with. So to convert to grams, we just multiply the mass by 1000, because 1000 grams, the kilograms means 1000 grams. That's what kilo means. That kilo part means 1000, so it's 1000 grams. So we then come to our formula, which is rho density is equal to mass over volume, which is equal to the mass which we have calculated there, which we have converted to grams there. You can just calculate straight away as kilograms per cubic kilometers. It's still fine. So after dividing the two, volume into mass, we then get 1.6378 grams per cubic centimeter, which is our rho, which is the mean density, to 4 decimal places. Okay, now let's look at Neptune's surface gravity. So like I said, now we're going to deal with a different approach to the variables that we're looking at. But first of all, we're going to be dealing with two important formulas, like we did with the speed. So the force of gravitation that you saw, the formula for that gives us what we call the Neptune, rather the Newton's. I don't know why I'm thinking of Neptune there. It's Newton's law of universal gravitation. It comes from that formula of F is equal to gmm over r squared. And you can read it to see what I mean. It basically talks about the proportionality of the masses, the product of the masses, with the square of the separation of those masses. And then we have mg, as you can see in blue there. That one is explained in the Newton's second law of motion, which says for a body of constant mass, its acceleration is directly proportional to the resultant force of that mass, which is basically F is equal to ma. And we see that when we equate the two, we're basically saying the forces of those two laws that we are seeing are equal in terms of that Neptune object that you're seeing there in that illustration. And that distance, again, I have made it a bit clearer now. In the previous videos, except for Earth, it wasn't clear what I meant when I said the distances from the surface inside into the planet. That's what I meant. And as you can see, you can even see the internal structure of the planet. So we then derive our formula for gravity using those two laws of those two forces. Okay, so when you derive the formula for the gravity, you then get G is equal to capital letter G multiplied by capital letter M over r squared. And as you can see in the note above, it says where G is the gravitational constant, the capital letter G, the small letter g is the surface gravity that we're trying to calculate. The capital letter M is the larger mass, which is the mass of Neptune in our case. Remember, previously we were looking at the mass of the Sun. But now in this case, it's the mass of Neptune, which is concentrated at the center by that blue dot that you see at the center there. And then we have the smaller mass, which is the mass of the object experiencing that force of gravity on the surface of Neptune. And as you can see, we have an inner atmosphere and an outer atmosphere, which means the ground that we see on these first 4 planets close to the Sun, for example on Earth, we step on the crust, which is ground basically. Unless if you're on water, you can't step on water and stay there on top of the water. You drown. In this case, it's basically atmosphere. It's not a ground like what we see on Earth. So when you try to stand on top of the outer atmosphere, it's like standing in air, you see. So you might fall until you reach the mantle. But I'm saying even if you're on top of the outer atmosphere, you will still experience this gravity. So we then say our calculator G is 6.674 times 10 to the power negative 11, and then our calculator M is the mass of Neptune, which you have seen even in our previous calculation when we calculated what was it? Density, exactly. When we calculate density, and then we divide by r squared. Our r will be the what? The radius which we were using, which we calculated using the formula of volume. We made r subject of formula, then we calculated the radius of Neptune. Don't forget to convert to meters when you're calculating. We convert by multiplying by 1000 because it's in kilometers, so we need to convert it to what? To meters. And then we get our value of the gravity as 11.2739. The gravity on Earth is 9.81. So to two decimal places, we then say our gravity of Neptune is 11.27 meters per second squared, or newtons per kg if you are using F is equal to mg. If you then say force over the mass, you then get newtons per kg, so you can as well say 11.27 newtons per kg. Okay, to make the video shorter, please just read what's here and get to understand what we mean by albedo of a planet. If you don't understand, you might visit maybe planet Jupiter or dwarf planet Eris. I would suggest you visit the dwarf planet Eris. That's where I clearly explained this phenomenon of the albedo. Okay, so how we calculate it, we say our absolute magnitude, which is the V band magnitude as well, that's what it's also called, which is h of Neptune, and d is the diameter of Neptune in kilometers. We then find our albedo. Those are the two variables that need substitution. As you can see, our h will be negative 6.94, and then our d is the diameter of Neptune, which is basically the radius that we found multiplied by 2. Then that's what you see there. Then you substitute those values, and then we square the answer to get 0.4348 is our albedo. And then that would be approximately equal to 0.435 to three significant figures. But I think according to other sources it was 0.442. For example, the NASA Neptune fact sheet, it said 0.442. So if you can see where I went wrong, or where my approximations were a bit exaggerated, then you just help us in the comment section to clear that out, so that we don't get worried about what happened here, or we don't confuse ourselves. Yeah, but that's basically how we calculate the albedo. Okay, so from the previous slide that you saw that the information said 0 is pitch black and 1 is perfect reflector for the range that we use. We're using this albedo formula. We find our values between 0 and 1. So if 0.5 is like half, it means it's half of reflection of the half of the light is reflected and half of the light is absorbed. In this case it's 0.435, which is less than 0.5. Even with 0.445, it's relatively the same. So we are saying that it does not reflect all its light, it reflects some, and most of the light is absorbed. That's what happens with Neptune. Most of its light that it receives is absorbed. I think it is the Jupiter video where I explained what black body temperature is, so that's what we're going to be looking at. It's basically the temperature that is expected to be felt on the planet, the exact temperature that is supposed to be felt on that planet without trapping of heat. So what we are experiencing with climate change here on Earth, it's a bit weird. That's not what we expect. There's a certain temperature that we are supposed to experience in the atmosphere, or rather in the environment, without the trapping of the heat that's happening. So that's what we're trying to calculate here. So we have our albedo, so it's now easy for us to calculate. So our formula is there. T is equal to the fourth root of L, which is the luminosity of the star on which the planet is orbiting around, which is the sun in this case, and we see the values there in watts. Watts is based on luminosity, is like the power of of the emitted light. And then we have that 1 minus the albedo, which we calculated, 0.435, divided by 16 pi multiplied by sigma, the small letter sigma, the Greek letter, which represents Stefan Boltzmann constant, which is there with its weird units there. And then we have the same major axis squared, z squared. And then we substitute those values, as you can see, and then we get 43.9975, which means our black body temperature in kelvins is 44.0 kelvins. You're going to see how we find kelvins as our answer, as our unit for the answer. We will look at that later on, but that's to one decimal place is 44.0. And then we see that our absolute zero is basically equal to negative 273.16 degrees Celsius. That's according to the convention by scientists. So when we extrapolate the pressure by temperature graph, we then see that our absolute zero, where there is zero pressure, it's a negative 273.16 degrees Celsius for the thermodynamic temperature and all those variables that we look at. But basically, that's how we come up with this value. When we look at kelvins, that is what brought kelvins into existence, this unit of kelvins. So we then use theta as our side of the formula so that we get the degrees, just trying to differentiate the two. So our theta will be equal to 43.9975 minus the 273.16 degrees Celsius. Then we get negative 229.162 yes, and then that's approximately negative 229.16 degrees Celsius to 2 decimal places. But you find that other sources like the NASA Neptune fact sheet says otherwise. It says the value of the black body temperature is 46.6 kelvins. You can convert and see what it is in degrees Celsius, but that's the values that I got. If there are any errors, like always, you just comment in the comment section, and then we'll see where I went wrong. It's very possible that I can do something wrong here. It's very, very possible. But nonetheless, we are helping each other to understand our universe. So let's get to learn more about the universe through this, through these exciting calculations. Okay, so to prove the kelvins that I was talking about, we can still use the same formula to calculate units instead of the magnitude. You can also use the formula to calculate the units. But what we have to do now is to eliminate the constants that do not have units and the other variables that just don't have units. We eliminate them. For example, the albedo, it has no unit, so we eliminate it. The one that was subtracting the albedo, we also eliminate it. The 16 pi, we eliminate that, and then we're left with what only has a unit. So that's why we're now left with the fourth root of the watts, which is for the luminosity L, over the sigma, which is Stefan Boltzmann constant there, multiplied by the same major axis, which is in meters, and then we squared because it was z squared in the formula, so we then say m squared, meters squared, or square meters, and then that will be equal to that. We then combine the denominator there, and then we cancel like terms, and then we get our fourth root of the luminosity over watts per kelvins to the power of 4, and then we rearrange that and cancel the like terms, which are the watts, and then we get the fourth root of kelvins to the power of 4, and then that will be equal to kelvins. So that's the way we calculate that. So it shows that you can use the formula to calculate the magnitude and also to calculate the unit. You can calculate units for those who didn't know. It's nice to learn. So now we have come to the end of the calculation section, and also just be good to others as we end this series. I just want to encourage everyone to be good to others. Let's also get to love these planets, like one of us said in the comment section on the Uranus video, in the YouTube comment section. Let's just get to love. Let's just love these planets and seek to know more about these planets, because maybe one day we might even go to Mars and stay there. We know some companies and some agencies are busy working on that. Those that are involved in the astronomy industry, they are busy working on that, and maybe when we get there, it will be good for us to have some knowledge of the place prior to our arrival. Yeah, so it's just good for us to know. It's really a fascinating industry, this one of astronomy. and later on we will have more people going to visit the space. We had some people visiting some 2 years ago, I think. Mr. Jeff Bezos and Mr. Richard Branson and their teams, the Virgin Galactic and the Blue Origin, they went to space, and we call it space tourism. There is a slide show that I created. If you check the blog of the Education, Arts and Creativity Paul, there's a blog that's on the internet there. You find the link in the description of the channel. You can go and see that analysis, quite an exciting one. But yeah, basically it's good for us to just love these planets, and also let us learn to love each other as human beings. We are different people with different backgrounds and different situations, but nothing hurts than loving someone and then end up getting hate from that person. So let's just learn to love each other. Let's learn to live with each other very well. But yeah, this is the end of the video. Let's enjoy the rest of the video. Rather, there's still more to come as we learn more about this planet. So cheers. More on Neptune. Around the Neptune.